Welcome. In this video, I'll be covering transient heat conduction, which is also called as unsteady state heat conduction. Now, in most of the applications, what we do is we apply steady state basics and we can easily analyze the heat which is flowing through from one surface to another surface. Like suppose you have radiations which are falling on the outer surface of the wall. Through this wall you have conduction and the time which is available for conduction is very large. Like suppose you have about 8 hours from morning to evening, during which the solar radiations falls on the wall surface and the heat is conducted from outer surface to inner surface. There you can apply the basics of steady state heat conduction. But let us consider a case in which you have a hot object which is placed in the water. So immediately this hot object which is placed in the water will get cooled. So there the time which is available is very less. So there you need to use the basics of transient heat conduction to analyze this system. So the objective of this video is to obtain the temperature distribution equation which can be used to analyze heat flow from the solid to the surrounding using lumped heat capacity approach. And then you also can use some charts, Heisler's and Grober chart, to obtain temperature at any location in the solid. So once this knowledge is acquired, you can apply it in analyzing heat treatment processes, or you can also use it in analyzing heating and cooling process in a solid. So what is unsteady state heat conduction? So in case of unsteady state heat conduction, temperature is a function of time. Obviously temperature is also a function of other parameters, but here we are going to consider the change in temperature with respect to time. So when you consider a solid, we know that from one surface to another surface, if there is temperature gradient, then there is also variation in the temperature from in between the solid. But if you have very high conductivity, like let us consider that the conductivity is infinite. So in that case, you will not have any temperature gradient across the solid. That means temperature at any location in the solid will be same. So with very high value of K, like suppose K cannot be infinity, but if you have very high value of K, like take the case of a copper, where you have conductivity which is around 400 watt per meter Kelvin. So there with high value of K, the temperature difference between the two surfaces, and if the surface or the width of the surface is very small, then in that case the internal temperature gradient can be neglected. So you can assume that the temperature throughout the copper surface or copper solid is almost same. Another thing is, if you have very high convective resistance like 1 upon HA, which is 1 upon heat transfer coefficient into area of the surface, if this value is very large as compared to conductive resistance, which is B by Ka, so if this value is very high, there also you can actually neglect internal temperature gradient. So firstly, what is done is we calculate the Biot number. Biot number is HLC by K, which is, if you actually elaborate this, then it will be conductive resistance by convective resistance. And this Biot number, which is also HLC by K, if it is less than 0.1, if you calculate this Biot number and if you get it less than 0.1, then in that case we can actually neglect internal temperature gradient and assume that the temperature throughout the solid is same. So this analysis where you have Biot number less than 0.1, there you can go for lumped heat capacity approach. So what is that? Let us derive that. So if you have a solid and if you know the volume of the solid, surface area of the solid, the temperature, that is initial temperature at T equal to 0 and surrounding temperature, and if you know the heat transfer coefficient, conductivity, right, density, specific heat, all these properties of the solid, if they are known, then we can use this lumped heat capacity approach. So what is that? So we have Q, which is equal to HA into delta T using Newton's law of cooling. So delta T is temperature of the surface minus surrounding temperature. So that is T minus TA. This HA delta T is the heat which is lost from the surface, which is also equal to change in internal energy of the solid. That means if solid is losing heat to the surrounding, the internal energy of the solid is reducing. So that is equal to mCp into dt by dt, change in temperature with respect to time. And the negative sign indicates that the solid is losing heat to the surrounding. So there is a sign convention which is used in thermodynamics. So Q, which is equal to HA into delta T, and this is also equal to minus mCp dt by dt, and m is density into volume, so that you can substitute, and when you equate it, it will be minus rho Vcp, change in temperature with respect to time, that is equal to HA into delta T. If I separate the terms, then I have dt by T minus TA equal to minus HA by rho Vcp dt. So this is just an arrangement which is used for separating the terms so that you can integrate. So once it is integrated, then you have log of, so integration of dt by T minus TA is log of T minus TA, and integration of this dt is T, remaining terms are constant, so they are taken as it is, plus constant of integration. So there, this constant of integration can be obtained by using initial condition, that is at T equal to 0. If I substitute T equal to 0, then T, that is the temperature of the surface or of the solid, is equal to T0. So if I substitute that, so this is 0, so this term will become 0, and T equal to T0. So C1 becomes log of T0 minus TA. So that is written here. So equation first becomes, this equation becomes, I substitute C1 as log of T0 minus TA. So it becomes log of T minus TA. This term remains same. This is equal to minus HA rho Vcp into T plus C1, which is log of T0 minus TA, that is substituted here. Arrange these terms, then it becomes log of T minus TA by T0 minus TA, that is equal to minus HA by rho Vcp into T. And if I take log on this side, it becomes exponential. So T minus TA divided by T0 minus TA is equal to e raised to, or exponential of, minus HA by rho Vcp into T. So this equation which I have obtained is the temperature distribution equation. What it means? So at any time T, I can obtain the temperature of the solid. So this is, T means the temperature at any time T. TA is the atmospheric temperature or surrounding temperature. T0 is the initial temperature. So if I know all these terms, that is, if I know H, then if I know the dimensions of the solid, so I'll get area, volume. If I know the density of the material, specific heat of the material, at any time I can get the temperature. Or if I know the, or if I want to obtain time to obtain certain temperature, that can also be obtained using this expression. So what is the application of this equation? So it can be used in designing the thermocouples. Like suppose I want minimum time for getting or for measuring the temperature, then what I'll do is I'll choose a proper material so that the response of the thermocouple will be less. Response time of the thermocouple will be less. So I'll choose that material in such a way that the thermocouple immediately will give you the source temperature. Wherever it is placed, it will immediately give you that temperature. Or if I want to know that if initial or source temperature is suppose 100 degrees Celsius, and I want to get the time during which thermocouple achieves 80 degrees Celsius, then I can substitute all other values and I can get that time. So this equation can be used in actually designing a thermocouple, because this area and volume, that will depend on the bulb of the thermocouple. So I can design it so that I get immediate response. So generally thermocouples, they are very thin, because this volume or area to volume ratio, that should be maximum so that time is minimum. This equation can also be used in analyzing cooling and heating of the solids. Like suppose I am having a hot object and I am placing it in a water which is at suppose 25 degrees Celsius. Initial temperature of object is suppose 100 degrees Celsius. Then what will be the time in order to achieve 100 degree or 80 degree Celsius in the solid? So that can be easily obtained, right? So any temperature which is required, that you substitute here and you will get the time which is required for attaining that temperature. So this equation is very useful as far as temperature varies with respect to time, and you can easily use this for getting that time. You can also obtain dimensionless form of HA into T by rho V Cp, which is the power of the exponent which we have. So HA T by rho V Cp, that can be written as, I am multiplying and dividing it by K. So H by K into KT by rho Cp, and I am taking this area in the denominator, so it becomes V by A. So H by K, KT by rho Cp, this written as it is, but V by A is called as characteristic length. If you divide this, you will get a characteristic length of a solid. So I'll substitute that V by A as LC. So now if I actually again multiply and divide this left hand side by LC, so denominator becomes LC square, and you have LC in the numerator also. So HLC by K, this term I am separating, and KT by rho Cp into LC square, which I have taken here and I am multiplying in the denominator as well. So this becomes LC square. So K by rho Cp is alpha. This is also called as diffusivity, thermal diffusivity. So alpha T by LC square, this is another term. So one term is HLC by K and second term is alpha T by LC square. So this term HLC by K is called as Biot number, where H is heat transfer coefficient, LC is the characteristic length, and K is the conductivity of the solid. And Fourier's number alpha T by LC square, it is written as FO, which is Fourier's number, where alpha is thermal diffusivity, T is the time, and LC is the characteristic length. So if I substitute in the earlier equation, temperature distribution equation, this HAT by rho V Cp can be replaced as Biot number into Fourier number. So T minus TA divided by initial temperature, that is T at time equal to 0, T0 minus TA, that is equal to exponential minus Biot number into Fourier number. So this is an expression which is obtained in terms of dimensionless numbers. Biot number and Fourier number, they are the dimensionless numbers. So what is that characteristic length? So as I told you, it is volume divided by surface area. So for a slab, you can calculate characteristic length as area into thickness. So area is the cross section area and thickness is the B is the thickness of the slab, divided by the surface area on two sides. Generally we are avoiding the thickness, since for a slab thickness is very less as compared to the cross section area, or the length and the height. Thickness is very less. So generally we are not considering that area, we are just considering the cross section area which is on both sides. So it is 2a. So this characteristic length for a slab becomes b by 2. That means if you have the total thickness of the slab as b, then heat can flow in both the directions. So LC will be like b by 2 in that case. So it can be understood like that. Similarly, for a cylinder, you have volume which is pi r square into L. So cross section area into L, that gives you total volume, divided by 2 pi RL. So circumference into length, that is surface area. So it gives you characteristic length for a cylinder as r by 2. Similarly, for the sphere, it is 4 by 3 pi r cube divided by 4 pi r square. So this is volume by area, which comes out to be r by 3. So this you need to remember: b by 2 for slab, r by 2 for cylinder, r by 3 for sphere. And if you have a cube, then L cube is the volume, and 6L square, there are 6 faces. So 6L square, that gives you L by 6 as the characteristic length. So this can be used in analysis. So you just calculate this separately, LC separately, and substitute in it in getting Biot number and Fourier's number. So if you have Biot number less than 0.1, you can apply the concept of lumped heat capacity approach in analyzing this system. There is another term which is called as response of the thermocouple, or response of any temperature measuring device. So response, as is defined, is time taken by measuring instrument to reach the source temperature. Like suppose you are placing thermocouple in hot water, then what is the time which is required for getting the exact temperature of water? Suppose it is 100 degree, then what is the time which is required by thermocouple to reach 100 degrees Celsius? So that is called as a response. So for rapid response, this term HAT by rho V Cp, this should be very large, so that the time which is required is less. So how it is achieved? So one thing is, you keep the diameter of the wire very less, or thermocouple very small. Cp value and rho value should be small, but H value should be very high. H value should be very high. So these things will give you high response, immediate response. I think I mean to say that it will immediately give you the temperature of the source in which thermocouple or any other temperature measuring device is placed. Another term which is called as time constant. So if you calculate or get the unit of rho V Cp by Ha, then it is unit of time, and you will get that as second, and it is denoted as T prime or T star, whatever. So if I use T equal to T star, then it is called as one time constant, and if I substitute that, it will be e raised to minus 1. So we have expression as T minus Ta divided by T0 minus Ta equal to e raised to minus HAT by rho V Cp. So it will become T by T prime, and if T is equal to T prime or T star, then it becomes e raised to minus 1, and this comes out to be 0.368, which means that the temperature difference, which would be temperature difference would be reduced by 63.2% in one time constant. That means this comes out to be 0.368. So in order to achieve this 63.2% of the temperature, initial temperature, you will require one time constant for a given solid. Now it is okay that if Biot number is less than 0.1, you can go for lumped heat capacity analysis or approach. But if Biot number is greater than 0.1, then what? So there are some charts which are available which can be used to obtain either time or temperature, and these charts can be obtained. These charts can be used to obtain temperature at any location. Like there are two charts which are to be used. First chart is centerline time history chart, and this was developed by Heisler. So what is that? On y-axis you have T0T, that means 0 in this numerator indicates x equal to 0. So at any given time, what is the temperature at x equal to 0? So that is denoted by T0T, small t, minus T infinity divided by T0 minus T infinity. The T0 in the denominator indicates the initial temperature, or you can use some other notation like Ti in the denominator, Ti minus T infinity. So initial temperature minus the atmospheric temperature. But in the numerator you have T at x equal to 0 at given time. So for that you need to calculate firstly Biot number and Fourier's number. So Biot number is HLC by K, and Fourier number is taken on x axis, which is alpha T by LC square. So firstly you get value of LC, from that you calculate Biot number and Fourier's number. So once Biot number is calculated using the expression HLC by K, you take the reciprocal of that value, which is 1 upon Biot number. So that value you have. You also calculate value of Fourier number. So using these two values, you will get this ratio from this graph. Like suppose I get a Fourier number of suppose 20, and if I have 1 upon Biot number as 4, so 20 and 4, if I use these two values, so I go up from this 20 vertically, and I have this 4, 1 upon Biot number as 4, so I go here, and when I draw a horizontal line wherever these two values intersect, I'll get the ratio of T0T minus T infinity divided by T0 or Ti minus T infinity. So once I get this ratio, like suppose I get this value as 0.01. So once I get that ratio, I then substitute initial temperature, atmospheric temperature, and I'll get temperature at x equal to 0 at given time. Like suppose I am asked to get the temperature at x equal to 0 at time equal to 1 minute. Then I substitute t equal to 60 in calculation of Fourier's number, and I'll get that value t at x equal to 0 at 1 minute. So this is one chart which is used for obtaining temperature at the center for a given time. Chart which we can use to obtain temperature at any location from the center. Like suppose I want to get temperature at x equal to 0.5. Like suppose I have a thickness equal to thickness of the slab equal to 1 centimeter, and I want to get value at any location between 0 to 1. Like suppose I want to get value at 0.5, then x by L in this that case is 0.5. So I know that ratio, x is any distance, L is the total thickness. So if I want it at 0.5, so one value I have 1 upon Biot number. I also have center line temperature T0 T at given time, T infinity is known. So at that location at 0.5 I can easily get this temperature using this second chart. So this chart, it can be used for obtaining temperature at any location from center line to the surface. I can also get the temperature at the surface using x by L equal to 1. I can also get temperature at x by L equal to 0.2, 0.4, 0.5, 0.6, any value in between 0 to 1. So these two charts can be used to obtain temperature at any location, or if temperatures are known, I can get value of time. So either ways I can use these charts either to get temperature or to obtain time. These charts, as I told you, are used if Biot number is greater than 0.1. If it is less than 0.1, we neglect the internal temperature gradient. We assume that the total solid is at same temperature and we use lumped heat capacity analysis. But if the Biot number is greater than 0.1, then we cannot use, or we cannot neglect internal temperature gradient. So we need to go for this chart, two charts, and this chart is available for a slab. Similar charts are also available for cylinder and sphere, and the x and y axis are same in those cases also. So you can use any solid and you can analyze that. Let it be a slab, it can be a cylinder or sphere, and you can use this Heisler charts and get the value of temperature or time, right? So thank you.